All right, here we go. 6.3, least squares regression. Line. So the textbook uses the acronym LSRL to refer to this thing that we call the least squares regression. Don't get hung up on the name of it too much. Know that if you just call it a regression line, that'll sufficient. All right. Maybe in algebra class you might remember we studied something called the line of best fit. This is the same thing. All right. We're going to use Desmos technology to enter data. This is not only going to create a nice picture for us, a scatter plot, but more importantly, it's going to get us what we know as the LSRL, the line of best fit, the regression line as we call it in stats class. Our example here is going to involve dog years and human age in years. So the first thing we need to do is take this data here and enter it into Desmos. Now, I've started this example off for you. If you go to Schoology and open this up, you will notice that there is a link to an example called human and dog years. So open Unit 6 and 6.3, and the last attachment there, it says dog and human example. Go ahead and click that open, all right? That's going to take you to Desmos, and I think I've already got it open. Now, yours is going to look different. Let me just start off with a new blank graph, okay? If you're doing a problem and you're like, how do I get a table? You just hit the plus sign in the corner and ask for a table, and voila, there it is. Your table is already partially filled. I think it shows the first 5 values like this one does. Go ahead and fill out the rest of the table. And again, if you just click on 33 and you hit return, it'll give you more spaces. So I think our next one was 6 and what? 7 and 41. Okay, so go ahead and type in a 7 and a 41. And take a moment. You'll start to see some dots show up here on the right. You might have to zoom your table out. Go ahead, use that minus key on the far right. That helps you see more of the dots. Anyways, I like to even scrunch it up and stretch the x-axis out. I know you don't have a touch screen, so you can't do that. Yours is going to look steeper. Not a big deal. It just makes the graph look different than mine. Okay, so you're entering data. As I'm blabbing away here, I'm going to go to my pre-filled data in. Okay, so there's all your data logged in. Again, you probably have to zoom out because you may be looking into this window here. You don't see much, right? So if you hit minus a couple times, it shows up. All right. Now we're going to take that information to a graph, and we also need to go to the equation. So let me go back to the notes here. We need to create a little picture in my homework that shows what I've got. Here we've got dog years. Is that right? Yeah. No. That's human. Sorry. Human. And dog years is the explanatory. No reason. I think we could have done it either way, human or dog. Depends just how you want to frame your question. All right. The first dot, I think, was 5.5. So my dog years, I think I can go by ones. Maybe? Got to get up to 11. I don't know if I have enough. 1, 2, 3, 4, 5, 6. No, I'm going to go by twos. So this is, and my y-axis, I'm going to go by tens. I think I can probably, no, maybe I'll have to do 20s here too. Yeah. Okay. So 0.5 and 10, or 0.5 and 5 would be something like there. 1 and 10 would be, oh, got that wrong. 0.5 and 10 would be there. 1 and 10 would be there. 2 and 19. 3 and 24. All right, you don't need to sit and watch me graph this. Go ahead and pause the video and make your plot of all these dots. Okay? 5 and 33. All right. I'm going to pause there. Next, we need to get an equation. How do I get the equation? Number one, on the computer, it's going to look like y1. In stats class, we don't call it y1, we call it y hat. All right? The computer's going to use a little tilde. So let's go and find our equation from Desmos. All right, notice down in the lower left, there's nothing below the table. So I'm going to come down here and I'm going to add an equation. So we start with a y and then a 1. And notice it's a subscript. Now the next thing you need to get is a tilde after that. You don't want the equal sign, so no equal sign, huh? You need the tilde. Go hit the keyboard, and then notice there's a tilde on the lower line. I think for you it might be a shift near the 1 or the 0. Mine's down here. All right? While you're there, go ahead and type an m, because we need slope. Do you remember that? We need x. So I'm going to go back here, mx plus b. All right, so we're going to type it in like we did in algebra days with those variables. Oh, I forgot one thing. Did you catch my little Minnesotan there? We need a 1 after the x. So go back there, click on that, need a 1. All right, as soon as you do that, if you got the equation typed in, you'll see a line show up. Excellent. We now have our linear regression. Notice down here in that lower left, I'm going to go back to my notes because I have this printed out in the notes and I need to kind of point to things. So we're done here, but know that below the table, this is where you get all your information regarding slope, y-intercept, and the r value, and sometimes even r squared. All right, here we go. So our equation looks like y equals mx plus b. Now statisticians sometimes go with a plus bx. Again, they're a little bit different from mathematicians. Notice here, the thing at the end that we call the y-intercept in algebra class has been moved to the front here. All right. Likewise, the m, which is sitting in front of the x, is now sitting in the b spot. So you can see that here in your notes on the lower left, how that equation sometimes gets flipped around on us. Fortunately, Desmos does it as like a math teacher would do, and so it's like you would normally see the M and the B. We want to report our results. So the first thing we'll want to do is write the equation out. Let's write down our values. So again, notice how we have M and B and R. Okay, so those are the numbers that we're going to report and use. And I've got to get them all on one page. All right, so here, R. R is something like 0.9907. So this is a really close fit. The M value, my slope, is 4.6418. And the y-intercept is 7,977,947. So now we can write the equation. Y hat is equal to the slope, okay, 4.64181 times x plus b, my y-intercept. And before I walk away from this, I need to interpret a couple things, the r value. tells me this is a really strong and positive correlation. My 4.64 is my slope, okay? And you remember that slope is rise over run. We might need to remind ourselves of that because I got to read my graph correctly. So it's y over x. So notice the graph is human years over dog years. Okay? So I'm going to take the human years over the dog years. And I'm just going to write words because I need to interpret the 4.64. So this is 4.64 human years per dog, singular now, year. And the y-intercept, 7.7947, is where we cross the y-axis. So this is, on the vertical scale, human years. Of these numbers, this last one is kind of the least useful. It doesn't really make sense if you think about it. But this one here is actually, the slope is fairly interesting and something we can talk about. Every 5 human years, or like 4.5 human years, is equivalent to 1 dog year. All right. Remember that before we can use the R value and say this is good, we need to check things. Is my data linear? Yes. Are there outliers? No. Is my sample size large? We have about 10, so it's not bad. It's not the best sample size. We should have more. And is it homogeneous? And the question is these two, even though they're both years, one refers to dog and one refers to human, so that's very different. All right, finally, we need to do, you need to learn 2 new words, interpolation and extrapolation. Interpolation, what does that mean? All right, here's our data set. Interpolation means that we are working within my data that I have graphed. So in terms of the dog, I am only working with data that's between 0 and 11. And humans have to go from 5 to 60 roughly. All right? So if you look at the graph, I have to have data that goes between here and here. So let's say we want to figure out, okay, I've got a dog at home. It's like 14 years old. How old is that dog? Well, if I put 14 in, hang on, my example is 6. Use the example, Mr. Larson, not your own one. Okay, so 6-year-old dog. How many human years is that? I go back, grab the equation. Y equals 4.64181 times x plus 7.7947. I'm now going to take the 6 and put that in for x. So grab your calculator, multiply 4.6418 times 6, add that to 7.7947, and tell me what you get. Hopefully you got something like 35.6. Reminder, that would be human years, right? Okay? All right. Now, if I were to reverse this process, be careful. If I was to do this with a 60-year-old human, I am now extrapolating. Notice the 6-year-old dog is interpolating because the 6 is right between my range of years that I have data for. But the 60 is extrapolation because 60 is out of bounds. Okay, way up there. So again, this time I'm going to plug the 60 in for the y. So now I got to solve. What x value would generate a value of 60? To do this, you're going to take 60 minus 7.7947 and then divide the result by 4.6 4, 6, 1, 6. Ugh, I wrote that down wrong. 4.64181. Okay? See what that gives you. I'm going to verify that on my calculator because it looks like I had some bad numbers in there. Okay, 64181. Okay, I get 11.2. So what you got? 11.2 dog years. Now we're on thin ice. Again, why are we on thin ice? Because we are extrapolating. So this is dog years. So a 60-year-old human, like Mr. Larson, is about 60. In dog years, I would be 11. All right? Again, extrapolation, muy malo, okay, bad. Interpolation, good. Why? Because you're staying within the data range. Now, notice R and R squared, okay? Look over here. There's the data set. Here we got R squared and R. This is just R times R to get that. And here, now I've got a really bad set of data, and look at R and look at R squared. See how much worse R squared gets? That's one of the reasons why we look at R squared, is that it makes R worse. Whereas if R is good, it tends to stay good, like in that previous example. All right? So another reason why we look at R squared as opposed to just R. Not a big deal, but just want to explain why it's there. Good luck in your homework.